okay? So let's recall our traffic light function and apply this to red. So remember, for our traffic light, red goes to green, green goes to yellow, and yellow goes to red. Cool, I got it right this time. F of 0 means not applying the function at all, so f of 0 of an element is always just going to be itself. But when I apply the red function once, so our function to red once, red goes to green. Now, if I take f2 of red, that's the same as taking f1 of green. So we're applying the function twice, so red would go to yellow. And then if I take f3 of red, right, that's really taking red 1, 2, 3, it's going to go back to red, and then red 4 would be 1, 2, 3, and then 4, and I would go back to green. So how can we define this pattern when f to the k of red equals red? When does f to the k of red equal red? Well, it repeats itself every 3 times. So if k is divisible by 3, f of k of red equals red. Or we could write this as f of 3 for some number. Let's let that number be n of red equals red. So it's cyclical, right? It follows a cycle, it repeats itself. Let's do some function iteration when it comes to our quaternion function, where we were taking g of x equals I times x. So remember that g of 0 of each element isn't applying the function at all, so it's just itself. It's kind of like the identity. Remember that any number raised to itself to the 0 power is 1 from college algebra. This is kind of the same thing. You just get yourself back. 1 is the multiplicative identity. Here we're taking the identity function, we get ourselves back. So that was a mistake. G of 0 just has each element, negative I goes to negative I, 1 goes to 1, very exciting, I know, and negative 1 goes to negative 1. So G of 0 has each element mapping to itself. G of 1, which we worked through earlier, has that I goes to negative 1, negative 1 goes to negative I, negative I goes to 1, and 1 goes to I. And if you've forgotten how we did this, please pause this and take a second to go through the work on these. I promise I'll do it for the next 3 graphs. But let's go ahead and graph G of 1, because that's what this was. G of 1 has 1 going to I going to negative 1, and negative 1 going to negative I, and then negative I going back to 1. What's G of 2 going to look like? So let's start by looking at G2 of I. If I look at my graph down here, I have that I originally maps to negative 1, but I'm applying this function once, so then I have I goes to negative I. Now if I'm looking at G2 of negative I have that negative I originally went to 1, but I'm applying it twice, so now it goes to positive I. G2 of 1, originally went to I, but we're applying it twice, so now it goes to -1. And G2 of -1, well, -1 originally went to -I, but then we apply it again, and it goes to 1. Okay, so here I had 4 loops for the identity function. Here I had 1 4 cycle. Now it looks like I'm going to have 2 2 cycles because I have -I going to I and I going to -I. I also have -1 going to +1 and +1 going to -1. Okay, what if I apply this function again? So let's look at G3 for starting out with I. So I have I. Let's look at our graph down here, right? I apply it 1, 2, 3 times. That means G of I goes to 1. Next, if I have G of 1, let's just substitute in 1. I have that 1 goes from 1, 2, 3, so it goes to -1. Let me clear this a little bit so that we can figure out more clearly where our graph is going. Okay. So if I have G of -1, that's going to go from -1 to 1, -I to 1, and then back to I. And G3 of I goes from to -1 to -I and then back to I need to know where G of -I goes. -I goes to 1, 2, 3. It goes to -1. And that means 1 goes to -I. That was a typo on my part. 1 goes 1, 2, 3 to -I. All these guys look really similar. So let's go ahead and make this graph. This is G3. I have 1. I have I goes to 1. 1 goes to -I. And -I goes to -1. And -1 goes back to I. So this is a reverse, right? We've reversed the direction. So G3 is the reverse direction of G1. Let's take a look real quick at what G4 would look like. I never have enough room, y'all. So G4 of I would mean that I goes from to -1 to -I to 1 and then back to itself. G4 of 1 would mean that 1 goes 1, 2, 3, 4. It's back to itself. So G4 maps every element back to itself. And we represent this. We'll do one final little graph. I goes to itself. 1 goes to itself. -1 goes to itself. And -I goes to itself. This is the same as G sub 0. Okay? So we could deduce that every time it's cyclical. If we applied it again, G sub 5 would be equivalent to G to the first, G to the 6th would be equivalent to G to the second. It follows this cycle, which is really cool and something to keep in mind. So just some final graphing definitions. A graph is connected if there's a path between any 2 vertices. It doesn't mean those 2 vertices have to connect exactly. That would be a complete graph, but it just has to be a path. So here's an example of a connected graph because I can get from any vertex to another vertex. Okay, so here's a connected 4 cycle, right? It's connected because there's a path from each graph. It would be complete if there was a path directly from each vertex to each other vertex. So this is connected, and this is complete. A graph H is a subgraph of a graph G if all the edges and vertices in H are also in G. So this would be a subgraph of this complete graph. I'll also draw in green. Here would be an example of a subgraph. So we could be H and the whole thing's G. If a connected subgraph that is not contained in any larger connected subgraph, it's called a connected component. So for your homework, it's in the text. It's pages 17 through 19. I'd like you to do problems 1, 2, 3, 7, 8, 9, 10, and 11. This is just going to help you get a really more of a hands-on feeling of how to work with discrete graphs. One thing I wanted to note, I'm going to talk about this a little later, but the set of natural numbers is typically denoted with this like in with a double line, right? That means a set of natural numbers. Remember, their natural numbers are also called our counting numbers. Those are the numbers 1, 2, 3, 4, 5, so on and so forth. So please shoot me an email or a message if you guys have any questions, and I'll be posting the next section shortly.